출석을 부르도록 하겠습니다. 자, 이재혁 씨, 고하늘 씨, 네, 고하늘 씨, 심준호 씨, 네. 이승빈 씨, 네. 이정태 씨, 네. 이충아 씨, 네. 충아 씨, 정상아 씨, 정상아 씨 안 계세요? 네. 홍주표 씨, 네. 홍주표 씨, 김민선 씨, 네. 김유신 씨, 네. 배민열 씨, 네. 배서령 씨, 네. 서하연 씨, 조대현 씨, 최승규 씨, 네, 네, 최승규 씨, 김성수 씨, 네, 미스터 마니케르, 오케이, 정상아 씨 아직 안 오셨나요? 오케이. Okay, so this is the lecture 25th and the last one in this semester. So usually in every semester we have 25 or 26 lectures. So I said this is more or less just a normal value. And yes, we are at the final lecture today. So how was your feeling about your midterm examination score? So some of you were a little bit disappointed, and some of you say that it's okay. So and the average value of your score is 71.8. So yes, so the full score would be 180. Of course, you say that, oh, my score is just 6 or 7. So, you know, since the system, our GEL system does not allow the maximum value exceed 100. So instead of this full score 180, so I just say 180 and I just say 18. So when you say you are 9, then it means that actually you have 90 points. So anyway, the average is not that high, but so let's go to our last lecture. So as announced already, so in next Monday you will have the final examination. So I think that the style is quite similar with that of our midterm examination. So please prepare your final examination in a similar way. And I found that actually some of you do not use even calculator because although your how can I say formula was correct, however the numeric value you calculated or you wrote was completely wrong, so you could not get the full credit about that problem. So have you used all calculators? Yeah, sure. So that is one thing, the bottom line, at least to attend this final examination you have to bring your calculator. So please give me the correct numerical value. So since this lecture it's not only for just science, it is for engineering. So number is quite important to all of us, not only to me, but also to you. Okay. So, any question from the students? So maybe I guess that you have tons of questions related with the midterm examinations, and yes, so I'm still okay. So if you have those questions, then please feel free to give me your questions. Then okay, so please. In principle, I should say yes. However, from my own practice, I usually do not give many problems already covered in our first part. So midterm examination. So I think that it would be better to concentrate on MOSFET and amplifier and inverter. So the later part are far much more important than the first part. So also I guess that actually, yeah, so deviation in the score will be even higher if we go to the final examination. So your grade will be more or less will be determined by the final examination, I guess. So so every semester we see this one. Every student learns equally well up to midterm examination. However, the real grade can occur only after the final examination is over. So don't be disappointed too much. So you have still chances to make over your mistakes, for example, or low score in final examination. And I want to once again stress that all of our previous examination problems are available to you. So reviewing or solving those problems is really up to you. So although I do not say you have to solve this problem or that problem, but I think that from the beginning of our lecture course, I just told you that every information is known to you. So please review our previous homework problem, or no homework problem, but final exam problems. Then you will get certain advantages out of it. So okay, so any further question? That was a good question. And any further question about exam or okay, then if you don't have any further question, then let me start the final lecture today. Okay, so in lecture 21st, we have introduced the dual device called PMOSFET. So previously we have considered N MOSFET, and this N was obtained from certain English word negative, and this negative is yes, of course, that is for our electrons. And here we have P, and you know that this P is coming from positive. So positive means that the carriers are holes. So holes are moving inside this transistor, and yes, since electrons and holes have the opposite charges, so reaction of our carriers with respect to certain voltage is actually the opposite. For example, when we have N MOSFET and when we have P MOSFET, and when we apply high gate bias voltage larger than 0, sufficiently larger than 0, and sufficiently larger than 0, then what will happen? In case of N MOSFET and P MOSFET, in both cases we have to have certain negative charges. Yes, here we also what happens? Okay, well, so here we have to have a negative charge, and even in this P MOSFET we have to have a negative charge. When you apply positive charge to gate side, then the opposite side, in the channel region, we have to have a negative charge. However, you know that this and that have different components. In the case of an MOSFET, here we can have many mobile carriers. It means that the freely moving electrons. However, in this case, in the case of a PMOSFET, that is just immobile ionized impurities. That's it. So in the case of our PMOSFET, although when we apply positive value, negative charges are collected here. However, that is not related with mobile carriers. That's the reason why when you apply positive gate bias, this PMOSFET can be regarded as off when VGS is positive. So that is completely different with our MOSFET. However, on the other hand, if we go to the other side, if we have a relatively low gate bias and relatively low gate bias, then things are changed a lot. So in this case, PMOS can collect holes in this channel region. So that's the reason why now PMOS can conduct the current. So I think that is not that difficult to understand this duality. So now let's think about the symbol for this PMOSFET and MOSFET. Yes, here we have a PMOSFET and MOSFET, and actually just using this symbol, yes, it's not possible for us to make whether that is MOSFET or PMOSFET. So people just to introduce an arrow to recognize its polarity. Yes, so you have seen it quite many times before. And let's just introduce another transistor called PMOSFET. So please note that the arrow has attached to this part. This part, yes, this part of MOSFET. And what is it? Is this the source or drain? So you can easily understand in the case of an MOSFET, this arrow was attached to its source. Then if we consider our PMOSFET, also we follow the same rule, same convention. Source should be denoted with our arrows. Then where do we have a source? This one is source or that one is source. So you know that from the viewpoint of a structure itself, there is no difference between source and drain. Actually, MOSFETs are symmetric devices. So the only difference between source and drain is whether some part is biased with lower bias or some part is biased with a higher bias. In the case of an MOSFET, if you apply low bias, that is working as the source. However, in the case of a PMOSFET, the terminal where the applied bias is higher than the other, that is used as the source. So simply speaking, what I wanted to say is this is source. The not low one but higher one is source. So if we just follow this duality, then please have a look at this one. Why do we have this kind of arrow direction? So it means that yes, here we have a source and current directions just follows this way. That is the reason why we have this direction. Then in the case of PMOSFET, how about the current conduction flow? Please note that when you measure the drain current, usually drain current of your PMOSFET have negative sign. So simply speaking, negative sign means that this is a positive direction for your drain current. However, that is negative in usual case, so current is flowing through in this way. So now one rule is anyhow we have to attach a certain arrow here, and if we just follow the current direction as a direction of our arrow, then we have to add our arrow in this way. Yes. So simply speaking, when you have a look at the symbol of MOSFET, the arrow just shows that, oh, whether this is a source, which one is the source, and the direction of the arrow means that whether that is really an MOSFET transistor or PMOSFET transistor. So do you have any question about this symbol? So now if you are experienced engineer, then now when you just have a look at those two graphs or those two symbols, then you can easily identify, okay, MOSFET is placed in a lower place and PMOSFET is placed in a higher place. Okay. So any question? So some of you are confused a little bit. Okay, maybe some of you can ask me, if we just rotate it, then how can we distinguish this and that? So even though when we rotate it about just 180 degree, but still we have a different direction. So in the case of a MOSFET, we have an arrow escaping from our device, and in the case of a PMOSFET, we have an arrow incoming arrow. Okay, so do you have any questions? Of course. Let me just come back to our previous discussion. Now we believe that there is a device type called PMOSFET. However, fabricating this PMOSFET only. Please think about this one. Just to consider a chip where we have only PMOSFETs. If you have certain fabrication factory, and now you have just fabricated PMOSFET only, you don't care about MOSFET, then how about the cost for your fabrication? Maybe that will be the same with that for NMOSFET. If you just fabricate only MOSFET or only PMOSFET, then the price will be quite comparable. But what I want to say is, in reality, in our semiconductor fabs, instead of just fabricating MOSFET or PMOSFET, instead of simultaneously both of NMOSFETs and PMOSFETs are fabricated at the same time. So that's the reason why instead of MOSFET or PMOSFET, we just call it as Cmos technology. So maybe you have heard about this name quite many times. So this C stands for complementary. So complementary means that here you have something and there is another thing which it can be dual to the original one. So here we have MOSFET, PMOSFET, they are complementary to each other. So the technology called as Cmos technology. And when we say that just a semiconductor, it is just says a Cmos technology. Of course, at the beginning of technology, so several decades ago, the major technology was not Cmos technology. At the time, people just fabricated only one transistor because to them, even fabricating one type of transistor costs a lot and it was sufficient for their purpose. However, they soon realized that fabricating CMOS is much, so MOS and PMOS simultaneously is much better than just using one type of transistor. Today, we'll talk about why do we have such a great benefit from fabricating both of MOS and PMOS. But please note that before starting our discussion, I wanted to warn you that there is always cost. What is the cost of having the CMOS technology? Of course, fabrication step becomes much more complicated than just a single type of transistor. If you have to carry only one Cmos technology, then yes, that is a relatively easy task. Or if you care about only PMOSFET, that is not that difficult. However, if you have to introduce both type of devices, then you should be really careful. For example, you fabricated, for example, once MOSFET is fabricated. Oh, well, good. After that, on the same chip, you introduce your PMOSFET. In order to this one, you have to do something to make it. And let's think about a worst case like this. Your already fabricated MOSFET is now damaged by your subsequent processes to fabricate this PMOSFET. Then what will happen? Oh, so you lose everything. So since this problem, fabricating this both of MOSFET and PMOSFET, is not that easy at that time. However, anyhow, the economic advantage was so great, or performance advantage was so great, so people dare to implement the CMOS technology. Okay, so now let's come back our beloved circuit, NMOS inverter. So the problem of this NMOS only technology is now discussed, and now you know that there is a load resistor, and here we have NMOSFET. Yes, so let's say that this is input voltage and this is output voltage, and we have drawn the voltage transfer curve of this sub-circuit several times. How does it look like? Yes, I have told you many times that here we have V in and V out. In the case of low input voltage, since NMOSFET is completely turned off, so now we have exactly VDD in this case. Okay, let's say that this is a threshold voltage of our NMOSFET. However, problem occurs when we apply VDD to our NMOSFET. Yes, now when we have VDD, of course, now we have a very good conductance, high conductance channel here. However, that is just finite value. So we have to consider the relative conductance between this RD and channel resistance. So the ratio between these two resistances will determine the output. Of course, let's say the ideal case, if this one has a much higher conductance than this RD, then what will happen? Then we will have the output value quite close to this this value, so zero value, idealized value. However, let's think about the opposite case. So let's say that conductance of our transistor, even at its highest gate bias, is just comparable with RD. Then what will happen? In this case, we will have a relatively moderate value, not quite close to ideal zero. So this is a bad situation. We don't want it, and we want it. So now, anyhow, even though we have different sizes of transistors, still it is true that in this NMOS transistor technology, we have a non-zero output. So think about this case. Well, now you have a VDD, and now say that you have a certain V out, and this is sorry, we'll use black here, certain VDD value slightly larger than 0. So anyhow, now we have this one. Of course, from the viewpoint of this a strength of output signal, logical signal, this is not a good case. We wanted to have the strict 0. However, this is not the case for our Cmos technology. I have stressed this point again and again. But now think about another point of view. Okay, so now when we have logical 1 as an input, then this Cmos inverter will generate logically weak 0. Okay, I see. And another point is, now think about the power consumption by this Cmos transistor when input is just logical high. In this case, now from the viewpoint of VDD, there will be certain current conduction. Okay, there will be certain current conduction. So now we can expect there really exists the power consumption. Then how large is it? So that can be given by just VDD multiplied by the amount of current. So what is the amount of current in this case? Of course, that is, here we have to have current, and that current would be just drain current of our transistor, or also the current of our resistor. Yes, in this case, drain current and the resistor current are the same. So are you with me about this point? So then when you have a look at this IR, resistor current, how can you represent our resistor current? That is exactly given by, here we have RD, and in upper part we have VDD minus V out. That is exact relation. And now we will say an approximate relation. What is approximation? Yes, VDD is given, and V out we don't know. But point is, maybe if we have done it properly, the output voltage is not quite close to VDD. So we can say that VDD is much higher than V out. So it is quite close to 0, although not exactly 0. So now we can say that although not exact, this is more or less given by this way. So are you with me? So of course IR is not exactly equal to VDD divided by RD. Yes, this is not exact, but you know, since output voltage in this case is quite small, so of course we have certain errors introduced 0.1 volt or 0.2 volt, but doesn't matter because you know this value is much higher, like 1.8 or something like that. So now we have approximate relation. So now let's think about the power dissipated by this current. Then you know that the power, approximated power dissipated by our voltage source VDD can be given by VDD squared divided by RD. So are you with me? So if you have any question about this procedure, then please let me know. So of course I'm not saying that this is the exact relation. Of course it's not. But point is, since we are just counting numbers and just estimating what happens to this Cmos technology, and we found that when we apply just a logical 1 to our Cmos inverter, this Cmos inverter really consume the power. That's it. So and then think about, let's make a really simple estimation about the power dissipated by this one. For example, let's say RD is 1 ohm, so 10 kilo ohm. We have used these values quite many times. So, and in order to make it everything simple, let's say the VDD is just happen to be 1 volt. Is there really 1 volt technology? Yes, there was, but you know, nowadays it's not. But anyway, just to make an estimation, then if we have just 1, and 10 kilo, then what will happen to this value? Power dissipation squared 1 and divided by 10 kilo, so we will have just 100 microwatt. 100 microwatt power dissipation by single 1 MOS transistor, and we just keep it as just yes, value, input value is just kept as just a logical one. Think about this one. Now you have one single MOS inverter, and you just say input is 0 and output is input is 1 and output is 0. That is quite normal and can happen every time. But this transistor or this inverter, very basic one, just consumes 0.1 milliwatt. Can you live with this kind of power dissipation? So think about your chip, entire chip. Then please visit certain manufacturer. Then watch. For example, you can go to certain well-known chip maker, and they always advertise that their entire chip with billion transistors spans blah blah watt. So please make a comparison with your single inverter power consumption and the entire chip's power consumption. You will find that this is a really ridiculous value. So we cannot live with this kind of huge power consumption. Maybe you may say that, okay, Professor, that was just obtained from your highly underestimated RD value. If we increase the RD, then, for example, if we increase this 10 times, then power will be reduced 10 times. Wow. No, it's not. So if you increase this one, then you have a serious problems about your transistor. I will explain it right now. So simply speaking, the failure or the reason why we don't use this single MOSFET transistor any longer is simply given by the fact that it consumes this power. So that is a critical point, really critical value, critical point. Our industry has evolved in this way. Due to this power consumption, industry has changed from single transistor to Cmos technology. More basically, more fundamentally, we have to say that transistor based on MOS technology, single type of MOS technology, was not the major technology. So in the history of our technology, the major technology was, even though we do not even discuss about that technology, however, there has been a technology called BJT, bipolar junction transistor. That was actually the major technology of our transistor industry for several decades. However, even in this case, this BJT has some power consumption problem. So that's the reason why now we have moved several decades ago. Now we have moved to Cmos technology. So power consumption is so important. So please don't be fooled by certain news found in the certain newspaper or something like that. They say that I have invented a certain transistor or blah blah blah. But point is, the most important one is this CMOS or dual device. The existence of these two types of devices is critically important. Without those pair of your transistors, then even your logic circuit with this simple configuration will consume tremendous amount of powers. So it's not acceptable for logic application. So please keep in mind that. I have told you that there are many semiconductor materials, and yes, there are actually many, but it is difficult to find this duality in real materials, because silicon has well-defined n-type dopant and p-type dopant, so they can have n MOSFET and p MOSFET simultaneously. But unfortunately, for many different good materials, but it is not easy to find this kind of duality. So, well, that was just a side story, and let's go to our main lecture once again. So now you realize that Cmos inverter structure is quite bad from the viewpoint of power consumption, DC power consumption. It just consumes the power, and we cannot use, you cannot make or design a cell phone with Cmos only technology. So we have to have better way. Then, okay, now you say that by increasing our, for example, resistor, then we can reduce power consumption. Then let's think about the extreme case. Wow, now you have really a huge resistor here, and now you have just a normal transistor here. Think about this extreme case. Then what will happen to your technology? Even in this case, when you apply VDD, then now your transistor is turned on, and since this load resistor is so, drain resistor is so high, so relatively this one, the N MOSFET, can provide alternatively good path to the ground. So in this case, if we have a huge RD in this case, then maybe we will have the output value quite close to 0. Good. Also, power consumption in this case also will be quite small, because R is so high. So according to this expression, so although VDD is given, but RD is so high, so power consumption will be reduced greatly. Good. Why don't you just use this one? But point is, things are changing. So what is the purpose of your digital system? Why do you use digital system? Every time you have time-dependent behavior, and following that time-dependent behavior, your digital system makes sufficiently good response to change. For example, I push something, or just push the button, then that is just converted into electrical signal, and that should be processed by our internal chip. So signal can change from 0 to 1 or 1 to 0. Now think about this case. Previously, we had logical 1. Oh, in this case, we have logical 0 quite close to 0. But happen to be, I just increase or change in my mind, and input becomes 1. Then what happened? Our ideal case, we have to have this 1. So from 0, it should change to 1. Of course, if we have just this N MOSFET only, then everything will be just fine. But you know that even when you consider our amplifiers, we always think that there is one stage of our interest, and there exists the previous stage and the later stage. So do you remember this concept? So here we have a certain amplifier of our interest. However, in the source part, we have to consider certain source, and we have to also introduce certain impedance. So this one just represent our former stages, and this one represent our later stages. So quite similarly, yes, here we have a single stage, single inverter stage. However, it does not exist only in the universe, there will be another stage. For example, let's think about the chain of inverter. What is a chain of inverter? So I will just write down here. If we have a chain of inverter, then we will have another inverter here. Yes, we can have this kind of a system, and this output is just connected to the input of the second inverter, and we will say that this is the real output. Then what is it? Here we just invert our input once, and once again it is inverted once again. So what is it? This 2 times inverted signal is just the same input is copied to the output. So this is just called as a buffer. So input is just copied into the output. Let's consider this one. Then, yes, previously when you consider this MOSFET or MOS inverter, then we just saw that everything is just isolated and nothing was there. But now, if we consider its later stage here, then what is seen from this output node? So, for example, yes, from this point, what is seen here? Now, following this line, you find that actually the capacitance of your second stage transistor. So, are you with me? Then, if you cannot understand, then although that is not quite correct, let me just think about the small signal model of this second stage. Then you can easily realize that this is the gate of your second stage, and now you have capacitor, and you have, yes, current, voltage controlled current source, and of course this is not very quite accurate because this is just a small signal model, but just to think about this just approximate way. Then from the viewpoint of your second stage gate, then you can see that there is a capacitance. So the capacitance of your gate. So from the viewpoint of your the central stage, all of these subsequent stage can be just written as a simple capacitor here, C. So what is the physical meaning of this C? Yes, that physical meaning of C is just the gate capacitance of your next stage. So now you have C here. Then now think about this one. More or less this C is have reasonable value because the size of your MOSFET is just reasonable. But now we assume that we have introduced a ridiculously large value for our R. That is now current assumption. Then think about this one. Previously, when the original value was, input value was 0, then output was quite close to 0. Oh, sorry. When input was 1, the output was quite close to 0. And now we suddenly change it to input to 0. So our output should be increases to logical 1. Then think about how can we increase the voltage assigned to this node. Simply speaking, when we have this NMOS inverter and attached to the load capacitor, then the output voltage is given by this capacitor voltage, and in order to increase this capacitor voltage, we have to provide sufficient amount of charges into this node. Then who can provide the charge into it. Of course, there are only two passes. One pass is N MOSFET, and another pass is R. However, in this case, please note that now input voltage is just 0, so N MOSFET is effectively turned off. It does not provide any current conduction error. So in this 0 input case, now we can effectively just neglect this guy. The system becomes just serially connected RC. Then now you know that it is simply given by this way. Now this system can be viewed as this simple system. Now yes, we have this serially connected R and C. Originally the value was 0, however it is abruptly changed to VDD. Then after long time has passed, then we eventually have VDD. That's true, but the time constants related with this time transient is well known as what? What is the time constant related to this circuit, RC circuit? The time is given by product between R and C. Yes, so multiple of this time constants, RC time constants, after 3 or 4 tau has passed, then now our output value is quite close to VDD. But please note that we have made a certain strange assumption that our R is quite high in order to make our power consumption low and also quite a strong output signal. So what happens if this R is too high? Then our tau will be too high. It means that it will take forever to charge this capacitor. It means that, oh, your object to take a picture is moving. However, your logic system, digital logic system, cannot process it in a reasonable time. So this time constant becomes too long, too high, if we have too large R. So there is a contradiction. Okay, so if we just consider this logical or DC static property, then large RD will be quite good. So with just a large RD, you can solve power consumption problem and also weakness of your output signal. That can be solved. However, that is just a way just to damage your speed. Your system becomes slower and slower. If you just increase 10 times larger resistor, then immediately you have 10 times slower system. Can you live with this slow system? Maybe not. So in any way, it is not very convenient for us to work with this NMOS inverter, where this upper part is just made of resistor. So now you understand. So I have made a long discussion about why NMOS inverter is so bad. But point is there any solution? Yes, solution is quite simple, and I will just immediately give it to you. So now we have a series of N MOSFET and P MOSFET, and now they share the input voltage, and yes, their shared drain voltage is used as our output voltage. So now we have tested our N MOSFET in 3 different ways. Do you remember? So First one was we just considered voltage transfer curve. So simply speaking, when we apply VDD, our output should be 0. However, MOS inverter was not very successful to have this beautiful voltage transfer curve. And second one was DC power consumption. Oh, we cannot live with this DC power consumption. However, unfortunately, our MOS inverter should consume the DC power. And finally, the last discussion was the speed of our MOS inverter. Especially the problem occurs when input voltage changes from 0, sorry, I made a mistake. When input signal changes from 1 to 0, then we have to have the charging our load capacitance. So we have to charging the load capacitance. However, that takes forever if we have a large R value. So let me just test or examine our MOS transistor according to these 3 criteria. Okay. So first one, voltage transfer curve. Let's just consider the case where we apply logical 1 to here 1. Then the ideal case would be just logical 0. Now let's think about this one. MOSFET. Yes, MOSFET, it contribute just as before. It can provide certain good channel. And think about our PMOSFET here. Yes, here we have VDD, and gate voltage is now also VG is also VDD. So then what is the VGS of your PMOSFET? Then VDD minus VDD. So you know this is your gate voltage for PMOSFET, and this is the source voltage of your PMOSFET. So in this time, maybe you can be a little confused. Always you saw that source is 0, but you know, in the case of a PMOSFET, source is always attached to, you know, this higher one. So in this case, VDD. So in this case, specific case, your gate to source voltage equal to 0. Then what happens? PMOS is turned on or turned off. Your PMOSFET is completely turned off. So now this guy is completely turned off, and when that is completely turned off, compared with our counterpart or resistor, it can provide us much higher resistance. That is the point. Yes, this guy MOSFET was there, and we have to make a relative comparison between our resistor and PMOSFET. However, when PMOSFET is turned off, then it can provide us much higher resistance than normal resistor. So that's the reason why when you make a comparison, then this MOSFET is greatly higher conductance than PMOSFET. So we can certainly sure that the output voltage when input equal to 1 is exactly equal to 0. So are you with me about this point? Now in this bias condition, when we apply 1 to our NMOSFET and PMOSFET, then NMOSFET is fully turned on. It shows its maximum conductance, and PMOSFET shows its maximum resistance. So now it's like this. Previously, it's like a certain system, and previously it was given, yes, this guy just represents a register, and only N MOSFET makes this comparison. Yes, smaller, larger, smaller, larger. That was the case. However, in the case of CMOS implementation, now both ends dynamically change. For example, in this case, yes, this is the system. When you have just a register, this guy does not change its conductance, and only MOSFET change its conductance. But in the case of a CMOS inverter, both of MOSFET and PMOSFET can change its conductance and exactly the opposite way. So they can give the dominance to another or another. So now voltage transfer curve consideration is verified. Then let's go to the most important part, second part, DC power consumption. Then now think about the DC power consumption in this case. What is the DC power consumption? It is equal to 0. Period. Because yes, although we have 0 here, drain voltage is 0. You know, in the case of our PMOSFET, VDS is actually quite high. What is our VD? Oh, sorry, I will write down here. So for your yes, when we just to calculate VDS, our drain voltage is 0 and source voltage is given by VDD. So our VDS value is just given by minus VDD. Oh, that is the highest value which can be applied to our PMOSFET. But point is, in this case, our PMOSFET is completely turned off. Although drain bias is high, but gate just prevent any kind of current conduction. So resultant current is just 0. No current error. So please, if you don't realize its importance, please always think about your MOS counterpart. Previously, your MOS inverter consumes the power corresponding to approximately VDD square divided by RD. That was its power consumption. However, now you have almost 0 power consumption. So that's the reason why we have to use CMOS technology. Otherwise, we cannot live with this high DC power consumption originated from MOS only technology. Okay. So do you have any question? So this point is quite important. No DC power consumption. That's good. That is actually the thing we have to realize. And finally, let's go to the speed. What was the problem of our MOS transistor? At the time, we had actually this type of equivalent circuit. Yes, suddenly we have changed our values, and it is now R and C. This RC time will determine this charging speed. But now think about this CMOS counterpart. Then how does it look like? Still, our N MOSFET does not play any role. It is just turned off. But now you can understand. Now this is V. This case, our P MOSFET is biased with 0 bias for our gate voltage, and it has now capacitor. That is the case. Now its source is tied to VDD, and its gate voltage is 0. Then what is voltage difference between these two? Yes, once again, VGS of our PMOS transistor is simply given by minus VDD, and this is the best condition for current conduction. And how about the initial value? Yes, since that is yes, so okay, so okay, so the input voltage is immediately changed to 0. However, previously the output was also 0, and now we have to charge it. So at the beginning of this charging procedure, both of our gate to source voltage and drain to source voltage are in both cases just minus VDD. So it means that this transistor, the PMOS transistor, is really maximally driven. It shows its maximum current it can deliver. So you know that this maximum current will increase the charging speed quite a lot. So you know that you can easily understand all of these conditions. Means that when we need low conductance, PMOSFET can contribute to low conductance. When we need high conductance, also the same PMOSFET can give us high conductance. That's the magic. In the case of resistor, resistor has the fixed value, fixed resistance value, so it cannot dynamically change its conductance. But fortunately, in the case of PMOSFET, when we need low conductance, we can just turn it off. And if we need higher conductance, then we can just turn it on. That is the magic we can enjoy out of this Cmos technology. So I think that this is one of very rare cases where engineering. So in engineering, in many cases, there are trade-off. If you change something, then something is good and something goes worse. Yes. However, in this case, CMOS technology in every aspect is much better than MOS technology. Of course, once again, all of this great improvement was obtained with what? Obtained with increased fabrication complexity. Your fab should do more effort to support this CMOS technology. It means that once again, you have to pay more to your fab guy. So, oh, I have a CMOS, then okay, I will increase the cost. Yes, then pay more and gain more from these technology advantages. Okay, so do you have any question about up to now? So at the second part of our lecture, I have tried to persuade that actually this introduction of PMOSFET, the dynamic change of conductance, can provide you much better performance from all kinds of performance metric. So now you can understand this is very good. And if you so I will wait for a while to receive your questions, and if you have no further question, then I will just give you a few comments on this one, then wrap up the entire semester. Okay. Any question? Okay, so if you are happy with this CMOS one, then now I think that my final topic maybe will be the how can I say once again power consumption. Oh, power consumption has been discussed already in the case of our CMOS inverter and NMOS inverter. So why do we care about power consumption again? In this case, now we wanted to talk about the switching case, switching power consumption. Now we understand if we have CMOS logic system, then we don't have any, how can I say, any DC power consumption. Once we set our input value, and it really consumes a very small amount of power. But you know, that does not necessarily mean that, okay, when you just 1, then you will have 0 without large power consumption. It's good, but it does not mean that when you change 1 to 0, you don't need the power. No, in this case, you have to spend your energy. Okay? So we will talk about this part. So switching really, even in the case of our CMOS technology, we have to pay our energy. So we will just consider this one. Here, now we have VDD. So let's have a look at from the viewpoint of our VDD. Yes, it has something. Oh, I have something, and there is also something, and yes, there is a load capacitor. That is a generalized view for our logic circuit. Okay, so you know what is it in this our simplest CMOS inverter? It can be a PMOSFET and it can be an NMOSFET. Of course, inverter is the simplest one in our logic family. You can implement NAND, nor any kind of logic implementation can be inserted in this part. So usually this guy, the lower part, is called as pull down circuit, and this one is a pull up circuit. So people say that there's a pull down and pull up. So simply speaking, it just this circuit provides the electrical connection between ground and our output voltage. So it tries to pull down the voltage. And also this guy have good conduction connection to our VDD, and it try to increase the voltage, so that is called as pull up circuit. But anyway, yes, let's have it. Okay. Anyhow, so okay. Okay, so now think about one step. So yes, this is the pulse we have applied to our system, and let's say that we have a constant or certain constant time difference between one pulse and another pulse. What is it? What is the English name for this time distance? That is called as period. Yes, we have one period and there is one pulse, let's assume. And if we call it as capital T, then of course we can think about its inverse value. Then 1 over T. So the frequency is given by just inverse of our T. For example, let's say that this is T is happen to be 1 millisecond. Then what is the frequency? The frequency is given as 1 kilohertz. So that is quite easy to understand. So now think about this one. Given one time period T, yes, time period T, then how much charge should be given to here. Yes, so the maximum charge we have to have when we have, for example, low, high, low. This is the behavior of our input, and the behavior of our output will just follow high, low, and high. That will be the amount of our charge. And in this case, the maximum charge at this point should be given by just C times VDD. So, are you with me? So, this charge, of course, the charge stored in this capacitor can be a function of time. Sometimes it can be 0, sometimes it can be 1. However, when we just consider one single period, so it is always can be think this way. So once, for example, let's think about this one. Once we have 0 value, after that we just charge it to its maximum value, and it's the end of our one single period. After that, it is just discharged, and now it is charged. So who charged this capacitor? Yes, yes, this VDD just to provide certain current to charge it. So then let's think about think about certain average charge. So during time t, how much the charge was supplied from this our VDD. In order to charge it, we have to have C times VDD. This is nothing but, this is charge stored in our capacitor, and that is supplied the time period of t. And now that is average current. Of course, you know that this isn't just an average one. However, we just have average current and time averaged one. And when we apply our VDD, current multiplied by our voltage, that is the power delivered from our voltage source. You know it. So it means that this amount of power is delivered from our VDD voltage source into the system. So simply speaking, 1 over T, how can you call it? So you know this is corresponding to your frequency. 1 over T is frequency, and C times VDD square. So you know that for a certain system, so in this case actually we have not used the property of this pull up device and pull down device. Even in this case we can use different configuration for pull up and pull down. The basic principle is just from the viewpoint of our voltage source VDD, it just gives charges to charge it. After that, it just discharge it. So this part, later discharge is done by this pull down device. But anyway, the total amount of power spent by our voltage source is simply given by this one. That's the reason why if you try to operate your system at high frequency, then you have a larger power consumption. Also, when you scale down your VDD, then you will get power efficiency. So VDD square. So if you just reduce the VDD by factor of 1/2, then you will get just a quarter of power spent by the same system. So that's the reason why in mobile system we are continuously reducing the VDD value. Yes. Okay, so time is already up and I have to wrap up right now. So thank you for your active participation in this entire semester, and let's have a look at next Monday in the classroom or examination room. Okay, thank you, bye.